Hello, hello, hello. Um, okay, that's annoying. Hold on for just a second. It's for some reason feedbacking into my. All right, there we go. Okay, so welcome to online calculus. Uh, I'd love to ask how everybody's doing. You can write how everyone's doing in the chat. Let's ask 1 to 5. How do we feel? Give me just a second so I can ask the question because I don't have the question up. This is all new for me. It's all new for you. Let's see. There we go. So 1 to 5, how do we feel this morning? Check it out. You can vote. So you can click on the numbers on Discord and vote. Yeah, cool. I didn't put pi up there. Sorry. All right. So the last time we were together, what was the last time we were together? Makes me sad. We talked about. I miss you guys horribly. So we talked about the minimums and maximums, and we talked about Fermat's stationary point theorem, and then we talked about the extreme value theorem. Okay. So last time we talked about min-max, Fermat's stationary point theorem, and the extreme value theorem. Does anyone have any questions about those things before we get started on new material? Okay. Today we want to go over the change in the change, concavity in the second derivative, et cetera, et cetera. Oh, I'm supposed to go over that's bad of me. I'm supposed to go over the problem set, aren't I? The quiz, aren't I? Quiz. Oops. I don't know how to do that on this computer. Okay, so this isn't working. That's wonderful. This is all new for me. Let's see. Ha ha ha. Okay, I made this work by going to the other screen. Okay, so the first question on the quiz was state the intermediate value theorem. Do 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 do. So this would be quiz. Ten B. Okay, so I can't get this to work at all. That's all good and fun. We'll come back to that. I wanted to go over the quiz, but I'll figure out a way to do it. We'll go over it next time. Anyway, oh, here it is. Okay, so state the intermediate value theorem. What was the intermediate value? Sorry, it was state the extreme value theorem. So it was let's do this. Let f from D to R, where D is an interval. Oh, I had AB on the thing, didn't I? I? 'Cause 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 I? 'C Yep, that's it. Then f of x as both a min or a max. Another way of saying that is the set f of x such that x is in a b as both a min and a max. And then the next question was the intermediate value theorem. Oh, 1 to 5. How do we feel about that one? So let me ask again. So 1 to 5, how do we feel about that? All right. I got a few ones. Lots of those. Lots of fives. A couple ones. All right. So the is this notation the thing that's confusing? This idea. Let's see if I can do this. This notation here. Can you all see the? Let's see. Is this the bit that's confusing here? This is just a set notation that says this right here. This notation here means the set of y values if x is between a and b, including the endpoints. Is that better? It's the set of all y values there. So our example was as follows, and forgive the glove, but it keeps me from this psychotic glove that you can't really see. But it keeps me from moving the screen around when I touch it with my fingers. Let's see. The example that we had was something like this here. Now, if this point here, let's blow this up. So if this point here, we'll call this A, and we'll call this point here B. These are in the X space. But the points, this set right here, this set right here is all the points that I hit between f of A and f of B. And it doesn't have to be right there, right? Because I could have this thing could dip down more. Is there a way to make that dip down without erasing the whole thing? Not really. So I could have a function that looks like this, where this is now the min, and this here is the max. But this set right here, these y values, is the set f of x such that x is in between A and B. So this is my set of x points here on the bottom, and this set up here, which I'm actually more interested in. So this highlighted bit here is the set of x's. That's an awfully big highlighter. But the orange bit is the set of y's, and the y's are what I'm interested in. Oh. Does that make sense? 1 to 5, how do we feel about that? Oh, let's see. Whole thing's cool, isn't it? Okay. So that's that image idea. That stuff in orange is that image idea. Okay. Intermediate value theorem. Okay. Okay, so the intermediate value theorem. What did it say? No, we care about the orange line on the. It's a good question. We care about the question is, so we only care about the orange line on the y-axis, or just the orange line that has the highlight over it? No, we care about the orange line that is on the y-axis, that entire thing. Does that make sense? Not the entire axis, but the entire orange bit on the axis. The highlight was meant to be the x space. So this highlight here was meant to distinguish where the x space was. And this orange bit shows us where the y is. That's a very good question. Okay. All right, so the intermediate value theorem, what did it say? I'm sorry, the stationary point theorem. Sorry. So Fermat's stationary point theorem. Okay. If f is differentiable at x, and f has a local extrema at x, then f prime of x equals 0. And you can also write this another way. You can also write it so also correct way to write it. You could also say the following. You could also say if f has a local extremum at x, then f prime of x equals 0, or f prime of x does not exist. And that's an equivalent way of saying that. How do we feel about that one, 1 to 5? Let's see if I can do this. Wait. Okay. So, excellent. I'm so happy there's so many people here. I really did think that, that this would be deserted. So it makes me feel good. Okay, so any other questions about that? Okay, so the third problem was a bit different, and I made a mistake on the third problem when I first posted it because I meant it to be the third problem as correctly stated is something like this. is this. And if you turned in the first version of the test, that was fine. But I did have a typo on it. It was meant to be the second. So the first thing said, explaining all your work, find the absolute min and absolute max for f of x equals x cubed on -1, 2. So for some versions of the quiz, so the original thing said -1, 1. I didn't want it to be -1, 1. I wanted it to be -1, 2. And I just, brain farted when I was typing it. And then I fixed it, but some people had already turned it in, so that's fine. If you had -1, 1, and then you answered it correctly, you'll still get full credit. Okay, but going back here, absolute min and absolute max for f of x equals x cubed on -1, 2. Okay, so what do I do here? The first step is to do what? Yeah. Okay, I could derive it or I could check the integral. Yes, I'm looking for critical values. First thing I'm going to do is I'm going to check the endpoints. Now, you can do this in different orders. This is just the list of orders that I had on the board. So I'll do it in that order. But you can just take the derivative, set it equal to 0, and then remember to check your endpoints at the end. I usually forget to check the endpoints, so I like to do it like so. Okay, so check the endpoints first so that I don't forget. Is that I do, okay, f of -1 equals -1 cubed, which equals -1. F of 2 equals 2 cubed equals 8. And then I'm going to take the derivative and set it equal to 0. Okay. So in order to take the derivative and set it equal to 0, I take the derivative and set it equal to 0. The derivative here, f prime of x equals 3x squared. So f prime of x equals 0. So implies that 3x squared equals 0, which implies that x squared equals 0 over 3, which is 0, which implies that x equals the square root of 0, otherwise known as 0. And the derivative exists everywhere because we've got a nice polynomial. So I've got no D and E points, so I throw 0 into, and 0 is in -1, 2. So we check it. Okay, so plug critical numbers back in to original. And I get f of 0 equals 0 cubed equals 0. So the biggest thing on the screen, let's see, these numbers are this one, and this one. Okay, the biggest one of those is we've got a max of 8 and a min of -1. And I could say y equals and such on, so forth and so forth. It's wrong. Okay, so how do we feel about that one? Okay, so there's a question. Someone's got a good question. Could I say x equals -1 and x equals 2? Those are the places where my min and my max are, but they aren't my min and my max. Okay, so I don't, they're not my minimum and maximum. Remember, the thing I'm interested in is this set here. The thing I'm interested in, dadgummit, is this set here. Right? I'm interested in the y values. Those are my mins and my maxes. Okay? Oops. So here, this 0, the biggest, right? And I'm trying to find my min and my max. Okay, so the question, so the 0, nothing happens. I mean, it's got an inflection point there, but it doesn't have a local min or a local max, and it doesn't have an absolute min or max. So this graph looks something like this. Right, and here is 2, here is -1, here's x equals 0, and so the biggest numbers, the smallest number is -1, and the biggest number up here is 8 on this interval. But both of them, I know I'm over, and my face is in the way. Both of them happen at the end point. Does that make any sense? So if I look at this graph above me here, the thing that's happening is everything's kind of just let me bring it back down so I can do that. So if I'm looking at this graph that's now on top of my head, right? That's the min, it's a y value, and the max is the 8, that's a y value. Any other questions? So yeah, so there's a question. Does an inflection point mean change of direction? No, it means change in the rate of increase and the rate of decrease. So we're going to talk about that today. It's not so much that there was an inflection point there. I could have had a number of other things happen. That's just what seems to be happening here. Yeah, so the 0 is, so there's a 0 in x space. That was a critical number. And so I used that 0, that number. So I use my critical numbers, I check them to make sure that they are not a min or a max. Because remember, when I had x squared, right? Let's compare this to x. So this was x cubed here. Compare this with x squared. X squared would have had this 1 here and gone up here. This would have been x squared. And so if I was doing x squared, my minimum would have been this 0 here. And my maximum would have been 4. So they can happen in the interior. This particular one, and I know I'm right in front of the thing again. That's going to take some getting used to. So here, the on this case right here, it didn't. I don't know why. Every time I touch the mouse, it wants to do that. This right here, right, had its minimum at 0 instead of at instead of at the endpoint. Does that answer your question? Okay. Are there any other questions about this? Okay. All right, so that's what happened last time. That was the quiz. Now, today we want to talk about the change in the change, which goes back to this question about inflection points. So we want to know what they are, and we want to know how they work. Okay? So here's one that's, talking about the change in the change. Here's something that's very relevant to our lives right now. Suppose I have a situation. So the change in the change. So consider a situation where there's an epidemic going around, okay? And every person, every period of time, so every day, an infected person infects one not infected person. So what does this look at? At day one, I have one person with the disease. So the number affected on day one is 1. Do we all feel okay about that? I mean, not okay, but, we start with one person with the disease. And then, so on day 2, he infects a person. And now we have 2 infected people with the disease. And then on day 3, both of these people infect another person. Does that make sense? We on board with that? Oh. So on day 3, person 1 infects another person because, he infected the second person on day 1, but now he's infecting another person. And the newly infected person, the person who was infected on day 1, now infects another person. So now we've got 4 people that are infected. And then on day 4, we've got 4 people running around, each infecting one other person. So now there's 4. Now we double it again, and we have 8 infected people, and so on and so on and so forth. So it only takes 11 days for us to get from 1 person to over 1,000. It only took 11 days. Okay? So, not, how do you feel? How do we feel comprehending this? 1 to 5. Not, how do we feel about the existence of this thing, running around, which is, of course, not a good thing. But the idea of what's happening is that every day I'm doubling the number. Yeah. So we have this function. Oh, I wish it would stop doing that. There we go. So this gives us our our function. Here it is, 2 to the x. Okay. So this function right here is f of x equals 2 to the x. Oops, wrong one. And I'm actually going to have to shift the scale on one without shifting it on the other here in order to actually see this function, because this function goes up very, 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 very quickly. And you can see here, I'm having to zoom it way out in order to see what's going on around day 10. And you can see right here on day 11, we're over 1,000. Okay, so that's the function 2 to the x. Now, the question is, this function is increasing everywhere. Is everyone on board with that? This function, the first derivative of this function is always positive. Okay? So, but it's even more than that. So I go over here. The first derivative of this function is always positive. So I take its derivative, d over dx. So f of x equals 2 to the x. And I take its derivative, and I get of 2 to the x equals ln of 2, the natural log of 2, which is just a number, times 2 to the x, which is always greater than 0. Moreover, this function, when I take the second derivative, I'm talking about the change in the change. I want to know how quickly that I want to know what's happening as I go on time to the change, to the steepness of the slopes. And if I look at this function, you can see here that the steepness is the steepness of the slopes. The slopes here are, well, again, I've got this thing. Let's see. I want to only increase the scale of. There we go. So if we zoom this back into our original kind of square scale, we can see that here the slope is shallower than it is here, and than it is here. So in other words, the slopes are, not only is the function increasing as I go along, it's the slopes are increasing. So yes, so the question is, can you explain real quick why we use this why we use ln for this problem? Remember the exponential rule. And remember that ln of 2 is just a number. I'm not actually using a natural log. That thing is just a constant. Okay? So if I just, ask Google real fast what the ln of 2 is, I actually will get a decimal expansion. It's just a number like pi. Okay? It's just something around, oops, I'm on the thing. So, let's go back to the tablet PC. Yes. So recall the exponential rule. This thing is just a number. ln of 2 is just a number. So this number here is approximately 0.69. Okay, that's kind of a, it's like pi is approximately 3.14. ln of 2 is approximately 0.69. It's just a number. Does that answer your question? So it's just a number, but it's always this thing, no matter what x is, f prime of x is greater than 0. But what I want to talk about is the slopes I have, right? But the point is here that the slopes are getting bigger, okay? So I want to talk about the second derivative of this thing. So this says my function is always increasing. But d over dx of d squared of dx2, 2 to the x, equals, well, the derivative of the first derivative, now remember that this number is just a constant, and I wind up with ln of 2 times ln of 2 times 2 to the x. In other words, I wind up with 0.69 squared times 2 to the x. And this is also always positive. So that tells me something about this function. This tells me that the function is not only increasing, this told me that the function was increasing. And this here, oh, you can't see that. This told me that the function was increasing. And this here told me that the function was increasing. In other words, the function is going faster and faster and faster and faster, right? And this is one of the dangerous things in epidemics. At the beginning of an epidemic, you get this exponential activity because it's curved up, and it's curved up in such a way, we call these types of things concave up, okay? So f is concave up at x if f double prime of x is greater than 0. And we can see that here. If we go back to our, let's see, if we go back here, you can see that it's kind of up here, right? There's this kind of up thing happening. It's concave up. And what that means is that the rate of increase is increasing. So 1 to 5, how do we feel about that? Let me ask the question again. So how do we feel about that? This idea that the rate of increase is increasing. Okay. Of course, this can't continue in a real epidemic, right? In a real epidemic, there are only so many people that can get sick. So what happens is that in a real epidemic, at some point, you run out of people that are still vulnerable to disease, right? The sick people, hopefully they get better, but once they get better, they're immune to the virus, or they didn't get better and they're no longer with us. But they're either way, they can't be infected again, and there's only so many people in the population. So what happens is that you get a curve that looks more like this. And this is sort of the classic S-curve. So what happens at the beginning is that people get infected and infected and infected. Let me do this here like this. So what happens at the beginning is that classic behavior we just talked about, where you have this exponential growth in the beginning. Okay. But at some point, I start running out of people that can be infected. So the curve changes. Okay. So how do we feel 1 to 5 about understanding what's going on here? How I get a lot of people infected, and then all of a sudden that I just run out of people that can get infected, and then of course everybody's got the disease at some point or had the disease. So this is not meant to model infected at any one time. This is the total number of people that got sick. How do we feel about that 1 to 5? Oops, wrong one. So this kind of situation where we just ran out of people to get sick. So there comes a point here where what happens is that it's accelerating and it's accelerating and accelerating. But at some point here, we have this point where we just started running out of people that weren't sick. And what happens then, so if you thought of this as a percentage of the population, sometime when about 80% of the population got sick at this point, on day 6, when 80% of the population was infected, we just ran out of people that weren't. We started running out of people that could be infected, and the rate of growth, it's always positive, but the rate of growth decreases. This is a model where everybody's going to get it, but the question is, at what rate is everybody getting it? Now, this has been in the news. The news keeps talking about flattening the curve. And the way that that's working is this. If I put some kind of modifier in front of this, times x, 0.05 might be too small. There we go. So when they're talking about flattening the curve, this is what they're talking about. By slowing the rate that everybody gets the disease, we stretch out the rate at which people get sick. It's not so much that we want to prevent people from getting sick, although we do, but when they talk about flattening the curve, they mean taking this exponential function and lowering the base. In other words, if we looked at our original one, where each person infected one person every day, okay? And we instead say, let's change the base. Let's say instead of infecting one new person every day, I only infect half a person. In other words, there's a 50% chance that every person who's currently got it infects a new person. And the curve flattens. It takes longer for everybody to get sick, especially if I can make it a 10% chance. So it's not so much that we reduce the number of people that got sick, although we will. We change the rate, the length of time it takes for everybody to get sick. And that's what they're talking about, flattening the curve. And that's, a side issue, but it's been in the news, so I wanted to talk about it. But when I flatten this curve, it means two things. It means, one, I've brought down so at any given time, if it takes 100 days for everybody to get it, that means that the hospitals were able to treat people and then get them out without overwhelming the system. So if I can stretch out the epidemic, I won't have what happens in Italy, which is everybody got sick all at the same time. The other thing that happens is that you move this point at which the rate of increase continued to increase. So now we've moved the point, we've now moved it to about 60% of the population, where now, because we're infecting fewer people, the rate of increase slows. And when the rate of increase slows, that's called concave down. So concave up is that the rate of increase is increasing, it's accelerating, which is actually exactly what it is. The second derivative is acceleration. So the rate here is accelerating, but the rate here, while still more people are still getting sick, but the rate of the increase is slowing down. The rate of the increase is negative. How do we feel about that? This idea that the rate of increase is negative. Okay. So let's take the derivative of this. Well, let's not take the derivative of that. That's just awful, right? I mean, we can. But let's take the derivative of something. Let's take the derivative of a slightly simpler function here. Let's take the derivative of this. It's the same S curve. I've just normalized it to 1, and I've kind of moved it around a little bit. No, it's negative. The second derivative becomes negative. So the question is it negative, by which I think you mean the second derivative? Is it negative or just a smaller positive number? No, it's actually negative. The change is positive, but the change is getting smaller and smaller. So the change in the change is negative. Convex, so there's also a question, is there such a thing as a convex curve? Okay, a convex curve is the same thing as concave up. So, you know, when I took calculus the first time, when Bush was president, the first one, H.W. Bush was president, then we talked about convex and concave functions. But now they want to talk about concave up and concave down functions instead of talking about convexity. So the new thing is to talk about different types of concavity. The convex is, it's one of those things where, you know how there were all these terms that have multiple meanings in math depending on which part of math you were in? This is one of those terms that has multiple meanings in mathematics, and, you know, people got together and said, hey, why don't we teach concave up and concave down instead, so that we have one fewer thing with multiple definitions? Yes, exactly. There's a comment that says concave up is a happy face, concave down is a sad face. And let's see what we mean by that. Okay. So I have this function. Let's do the easier function. Let's do this function. Let's do an example. And let's do this one. Let's do the function 1 over 1 plus e to the 2 minus x. You see. Okay. So let's do this function f of x equals 1 over 1 plus e to the negative 2x. And let's take the derivative. So if I take the derivative of this, how do I do it? What's the rule I use? Remember this one? The reciprocal rule? I do, okay, so I do f prime, negative f prime of x over f of x squared. And this would not be, let's do this as u, negative u prime over u squared, where this is u. So I wind up with, so negative u prime. So negative, the thing on the bottom here is, if you can see it here, 1 plus e to the 2 minus x. So this is negative d over dx of 1 plus e to the 2 minus x over 1 plus e to the 2 minus x squared. And that is going to be, well, the derivative of 1 is just 0, so that's nice. So I've got negative 0 plus d over dx of e to the 2 minus x all over 1 plus e to the 2 minus x squared. By the way, this bit is baggage. All right, this 2 minus x, I'm going to make that u. And my head is blocking it again, isn't it? I'm sorry, I'm going to make this v because I already chose a u. And I wind up with, let's see, I wind up with negative, the 0 goes away, e to the v times d over dx of e times d over dx of 2 minus x. Yes, I could. So the question is, could I change it to a negative exponent instead of using the reciprocal rule? Absolutely, I could. And you'd wind up with the exact same answer. You just do a chain instead of the reciprocal rule. And we need to carry our baggage. And that would equal e to the negative e to the v was 2 minus x times the derivative of this is going to be negative 1 all over 1 plus e to the 2 minus x squared. And this winds up being e to the 2 minus x with a positive sign over 1 plus e to the 2 minus x squared, which is always greater than 0. Okay, I don't know why this thing is doing this to me. Okay, so how do we feel about this right here? I've got something that is greater than 0 for all x. My tablet is starting to overheat, so this is going to be a problem. And so this function is always increasing. And if I go back to what I was looking at before, we can see that here. This function, this function is always increasing, okay? But it's got a change in the rate of its increase, okay? Right here, something funky happens. It goes from being concave up to being concave down. In other words, the rate of increase slows. And to show what that means, let's take the second derivative. So let's take the second derivative of this. So let's do f double prime of x, which is going to equal d over dx of e to the 2 minus x over 1 plus e to the 2 minus x squared. Is there any way to simplify this? No, because if I do that, I'm basically stuck with it, it looks like. Okay, so how do we take this derivative? What do I need? Anyone want to say it in chat? Excellent. Quotient rule, then some chain rule and stuff like that. So we could do all that. Yes, well, don't feel bad about spelling quotient rule wrong. It's a hard thing to spell. Okay, so we look at this. And I'm going to call this whole bit here nothing because my computer is now completely not working because, oh, that's good. Excuse me. Talk amongst yourselves for a moment. I'll delete this from the video, I suppose. Everything is broken, including apparently my monitor. Okay. All right. Let's see if this thing will come back alive. I may have to go get an ice pack for it. All right. So I have that. If I do the quotient rule, I get, we can call this something. We'll call this right here U. We'll call this right here V. And I've got that I need U prime V minus all right, so I've got a time limit on the technology, it appears. I am sorry. Oh. Give me a moment. I'm switching to plan B. Um, all right, we're back in business. Okay, minus V prime U all, all over V squared. Everyone on board with that? Now that I've got it working again. Um, so yeah, so anyway, the technology, this XPin thing, which I'm sending back, XP pen, is supposed to be the backup plan on the tablet when the tablet gets upset because it overheats. But apparently it's not, it's kind of a poor substitute for the working thing. Um, and okay, so it's maybe what I'll do for the next before the next class is go get an ice pack for it because it needs help. Uh, okay. Glorious. Okay, so coming back here, what's the derivative of this top piece going to be? Yeah, we just did it, right? So it's going to be, all right, so it's going to be negative e to the 2 minus x. Stop that! Um, 2 minus x times the bottom. Well, you know what? Forget it. Uh, okay. Well, let's see if this thing will come back up again. Okay. Well, it's not working. So I'm going to go stick my laptop in the fridge. Anyway, I take the derivative of this thing, and I wind up with this horrible thing. Just that $400 something. You think the damn thing would work? Okay, so all right. Well, I can't make it work. Anyway, what you do is you take the derivative of the thing and set it equal to 0. And that gives you suspect points. So the critical values of the first derivative where f double prime of x equals 0 or does not exist gives you places to solve for the inflection points. Okay, so what you do is you take the second derivative and you set it equal to 0. And then what you want to do is you want to find the minimums and maximums of the first derivative. So the inflection points are the minimums and maximums of the second derivative. All right, and so what I do is I solve for those points, and then I find where I solve for the minimum and maximums of the second derivative, and that tells me where this behavior changes. So if I go back to my thing, yes. So in chat, the solution is being posted by one of your compadres, whose name I will not mention because I'm streaming over a public forum. But if you look in chat, there's the solution that she's working out much more easily than I am. And for the next class, I will work this out ahead of time on Maple. Anyway, so I take that second derivative, and I wind up with a place where these inflection points occur. So if I look at this graph, it's going to be somewhere around here. Now, if I look at the graph somewhere around here, now let's do another one. If I look at this graph here, x times e to the negative x. Now, I work out its solutions, and it's going to have the thing here. So actually, let me go ahead and put this here, because that's actually, before I do that, let me put in this derivative here that we found for the other one. So this was the thing we found to be the derivative. Okay, so this was the thing we found to be the derivative. And if I compare that to this point here, to this graph here, we see that at 2, at x equals 2, right, where the derivative has been maximized. Here, the derivative, right, the derivative is now decreasing. So on my original function, the change is still positive, right? The derivative is still positive, but the change of the derivative is now negative. So when I take the derivative of this function, which is what we were trying to do before the whole thing melted down on me, if I took the change of that, I could solve for the point where the derivative changes. And that's called the inflection point. That's the point where people were getting sick. They're still getting sick. There's still more people being infected. But the growth, the rate of growth of the function is now slower. And as I move in time, it gets flatter and flatter and flatter. Now, if I think about this in economics terms, that's called diminishing costs, or diminishing marginal costs, or diminishing marginal returns. How do we feel about that 1 to 5, besides the fact that I can't seem to get anything to work? How do we feel about this concept that I can solve for the inflection point, that I can solve for the place where the derivative changes? Okay. So once I solve for that rate there, I can find where these inflection points, and I then can talk about the characteristics of the function. So why don't you play here? Oh, wrong screen. So here, play with this function here. Where does this function have a maximum? So here's the question. Let me see if this works again. I did what you always do with a Windows machine. What do you always do with a Windows machine to make it work? Besides check it out the window, right? I turned it off and I turned it back on again. So let's see if it works. My tablet. Yay! Okay. So play with this function. So here's the kind of two problems. Play with that function and then play with f of x equals x cubed minus x squared over negative 3, 3. Same thing. Find the max, min, and inflection points. Okay. Yeah, but now I moved it again, right? So now my head's no longer covering it. Okay. So play with those two functions and okay. So there's a question asking me, can I explain the steps to solving the last problem? So the steps for following the last problem. The first thing I want to do is I want to take the derivative. I want to first throw in the endpoints, find out what theirs are. Then what I want to do is I want to take the first derivative and see where I have other possible mins and maxes. Then I want to take the second derivative and find out where I have minimums and maximums of the first derivative. Does that make sense? Okay, so let's write this out as a sequence of steps. Okay, now what I'm trying to plug into the second derivative, I'm trying to solve for where the second derivative is 0. So essentially, I'm doing the exact same thing. So, well, let's talk about this. Okay, so a function like 2x squared minus 8 is going to be very boring because it's a parabola. It's not going to have any inflection points. So it's a very good question. The question is, can I do a simple function like 2x squared minus 8? And the answer is, that's actually a little bit too simple. So if I throw that in, and I'm already out of time, so let me just throw that one in there and show you what I mean by it's a little bit too simple. So if I throw in here 2x squared minus 8, okay, I'm going to wind up with a parabola. Okay, but if I do a function like this one that I just gave you, x cubed minus x squared. Okay, now if you zoom in on this function, and really these are kind of boring endpoints. The endpoints here should actually be -1 and 2. So let's change this. So if I talk about this function over -1, 2, so what I just did was I changed the wrong screen. I changed the thing to ask the question over -1, 2 because that's a much more interesting place to play with. So what I'm going to want to do here is I want to take this function here. Oops. I want to take this function here from x cubed minus negative x squared. And when you do that, you're going to find that it has a maximum here. It's going to have a local minimum here, a place where the derivative is 0, and it's local. It's not the biggest game in town, but it's the smallest game in town, but he's the smallest guy in the neighborhood. And then what I'm going to do is I'm going to solve, and you guys talked about local min and local max and the difference during peer leading last time, yes? So 1 to 5, how do we feel about the concept of local min and local max? Okay. So we talked about local min and local max last time. So what's going to happen here is you're going to find out where this thing has a local min. Now, the point is that when I take the derivative of this, okay, now when I take the derivative of this, something very interesting happens. Where this derivative is 0, those are the places where I suspect I have local mins and local maxes. So the green function here is the derivative. Now, when this function here has a local min or a local max, the derivative has a local min or a local max, that means that the parent function, the function above, had an inflection point. How do you feel about that 1 to 5? Okay. All right. So we'll pick it up there next time. I'm over time, and I'm sorry. If you have any questions, I will have office hours virtually after the next class. You can also you're welcome to hang out and watch the next class's video. But that's all for today. Next time, first of all, I'm going to throw my PC in the fridge before class so that it doesn't overheat on me again. But this time, what we talked about was the change in the change, and we talked about I hate it when it does that. The second derivative in a concavity, and we talked about these inflection points and computing them. We find the places where the first derivative has a min or a max. On Wednesday, you notice that I skipped section 4.2. I'm going to go back to that on 4.2, and we're going to talk about proofs by contradiction next time, and then we're going to come back to 4.3 again. So we're going to spend so I should actually write this here, right? So we're going to spend another time. So we're kind of going to skip around a little bit. We're talking about this one today because it's the other core. Then we're going to go back and we're going to talk about 4.2, which is and proofs by contradiction next time. And then on next time, then we're going to come back on Friday. You're going to do peer leading on the mean value theorem, which is the rest of the stuff in 4.2. And then on next week, on Monday, we're going to come back to 4.3, and we're going to do more examples of 4.3. And yes, I was trying to do cool things, so with talking about diseases and stuff, so it's relevant instead of doing easy examples. Yes, so there's a question in chat. When the first derivative has both a min or a max, there is an inflection point. When it has either a min or a max, there is an inflection point. That's a good way to put it. Any other questions? Okay. If you want to stick around for the 11 o'clock show, it'll be pretty much the same thing, except hopefully there'll be fewer technical issues because I'm about to go stick my laptop in the fridge. Otherwise, you're welcome to ask questions, and you're welcome to ask questions in chat and hang out in chat channel. And I will see you guys on Wednesday or in office hours later on today. That's it for me.